Hey everybody, today we're going into section 10.5, inferences for two population means using paired samples. Now we've only got one section to do today, and I'll give you a couple examples in here. But what distinguishes this from sections 2.3 and 10.2 and 10.3 is before, when we had with two sample t-test, we had independent samples. What it means is two samples are independent. Back to what we talked about a long time ago about independence, way back around the time of our first exam. Two samples are independent. Remember, that means if the selection of one sample does not affect the selection of the other sample. Okay, so that was from sections 10.2 and 10.3. Let's even just put a 10.2, 10.3 here. In 10.5, now we're using paired samples. So in 10.5, paired samples. What that means, the samples are related to each other. Oops, it's not a very good related. So the samples are related to each other. In other words, not independent. There, the are is they are dependent. In other words, the selection of one sample depends on what the selection of the other sample was. Okay, so it's very important to make this distinction because we do a completely different test. Our hypothesis test will be a single t-test. Notice it's not a two-sense, just a t-test using the paired differences. I didn't say paired. I said it, didn't write it. Using the paired differences. And so you'll see that as we do a couple problems, what we're talking about. Okay, so it's just t-test, not two sample t-test as we were doing before. We will have two samples, but since they're related samples, we can't treat them as independent samples because they're not. Okay, so there's the basic idea, and let's just jump into a problem. So let me pull a problem out for you, and we'll talk about what we're going to do here. Okay, so the way our author does it, which I'm not a huge fan of, he's going to state the null and alternative hypotheses just like we did before. So let me pull out a problem. We're going to start with problem 10.160. So let's scroll this up a little bit. We'll put the problem right here so that we can see it, but let me go grab that for you. Let's find my file. It's not there. All right, I can just grab it from here. Hold on just a sec. Bear with me. So documents, it's on my desktop. And it's in my statistics problem. Okay, so we're doing 10, 160. So let's pull that up. All right. So here's our problem. That's really not what I wanted to do, but we will copy this. And then we'll just go paste it on our sheet. Okay, so we're good. So we're just going to paste this problem in here. Paste. All right, so there's our problem. So a lot of words, let's kind of read through it kind of quickly. It says cooling down. Cooling down with a cold drink before exercise in the heat is believed to help an athlete perform. Researcher Jay Dugas explored the difference between cooling down with an ice slurry or a slushy and with cold water. In the article, ice slurry ingestion increases running time in the heat. I wonder what the conclusion is. Male participants drank a flavored ice slurry and ran on a treadmill in a controlled, hot, and humid environment. Okay, let's pause for a minute. We have 10 people doing this. They have cold water or they have ice slurry. They're connected because it's the same person that drank the cold water one time and the ice slurry the other time. So these are dependent. Whoever subject one is the same person in cold water and in ice slurry. So both times, that's why this is related. It's not 10 random people drank cold water and then 10 random people drank the ice slurry. That's not what we're saying. If that were the case, if we had 10 different people doing the cold water and then 10 different people from that doing the ice slurry, then it would be a 2-sample t-test. This is just 10 people doing 2 different things. So it's a paired t-test. All right, so anyway, 10 male participants drank a flavored ice slurry and ran on a treadmill in a controlled, hot, and humid environment. Days later, the same participants drank cold water and ran on a treadmill in the same hot and humid environment. The following table shows the time it took to fatigue on the treadmill for both the ice slurry and the cold water. So they give us the data. At the 1% significance level, do the data provide sufficient evidence to conclude that on average, cold water is less effective than ice slurry for optimizing athletic performance in the heat? And then they say, notice the mean and the standard deviation of the paired differences are negative 5.9 minutes and 1.6 minutes respectively. We don't care because we're going to have the calculator do this for us. Okay, so we do our null and alternative hypothesis. So we start off like we usually do, the null hypothesis. Now we're looking at the 2 different, so we're still going to go mu1 is equal to mu2 is going to be our assumption. And then the alternative hypothesis is just, well, what they say, that cold water, that's population 1, is less effective. If it's less effective, they're going to run for less time. So in this case, we'd say mu1 is less than mu2. So the average time to fatigue with cold water is less than the average time to fatigue with slurry. There's our hypotheses. Now, what we really need to do is we need to get another column over here called the differences. And that just means we're subtracting these 2 numbers. And so what we're going to do, we're going to have the calculator do this for us. So I will show you that in just a second. All right. So since these are not independent samples, use paired t-test. All right, so let's go to the calculator. I'm going to input all of those numbers. I'm not going to do the 1 through 10. That's just signifying who they are. It could be 10. Those signify anything else, but I'll put the columns for the cold water and the ice slurry. So let's jump here. Let's go new share, and we'll pull up the calculator. And you guys are, there it is. I was wondering what was taking so long. Okay. So we've got that. I'm going to go in and I'm going to put the into each of these sections. So let's see. So let me go over to list 1. You can see list 1's already blank. Wait, where'd list 1 go? Oh, how did I get over there? Get back to list 1. There's list 1. Go down. That's what I wanted to do. Okay. We have 52 37, 44, 51, 34, 38, 41, 50, 29, and 38. All right, so there's those 10. I'm going to go over list 2. I'm going to do the same thing. If I just arrow down, it'll pull me up to the top. Well, we see there's 10 in there. I'm not even going to clear it out. I'll clear it out. I don't want you guys to get any bad habits. All right, so we've cleared list 2. By the way, if you accidentally delete the column, I made a video. You can look for it on YouTube, on my YouTube channel, where I show you how to put the list back. Okay, anyway, we've got 56, 43, 52, 58, 38, 45, another 45, 58, 4, and lastly 44. All right, so everything looks good. Everything's nice 2-digit numbers. So here's what I'm going to do. We need to find the differences in these. One of the ways to do it, we could have done 52 minus 56 or 56 minus 52, it doesn't matter, and gotten that either as a 4 or a negative 4. We just need to be consistent. So you could have subtracted these either in your head or on a calculator and done a little list over to the side where you said what the difference was. What I'm going to do is I'm going to let the calculator do it. So these are easy enough numbers that you could have subtracted them yourself, but let me show you how to get the calculator to do it in case these were worse numbers. We would probably want to do that. So I'm going to arrow over. I'm going to go up to list 3. We haven't seen this before. This is a nice little trick. If I go into list 3, I can tell it what I want in that list. And what I'm going to do is I'm going to have it do list 1 minus list 2 to figure out what the differences are. So I go in and I go second, list 1, notice above the 1 is an L1, minus second L2 for list 2. And then when I arrow down here, bam, it does it all for me. So notice, since I used list 1 first, when I subtracted, that negative means whoever this first person is, they lasted 4 minutes less with the ice water. The next person 6 minutes less, etc. And notice they're all negatives. So everybody lasted less time to fatigue with the cold water. So anyway, what I'm going to do now is I'm going to do my hypothesis test on list 3. Now, if you had calculated those numbers, those differences yourself, then that's all you would have to put in, and you'd probably just put them into list 1. You'd say, oh, here's the differences. Let's put those into list 1. That's a perfectly fine way to do it. Here's where you have to be careful, though. Since I put them in list 3, when I do my t-test, I have to make sure to tell the calculator to use list 3. So I'm ready to do the calculation. We already have our hypotheses set up. So now I go stat, but notice when I go test, it's not a 2-sample t-test, it's just a regular t-test. So go down to 2, pick t-test, and the mu sub 0 here, think about what's happening. So we're doing this. We originally we said in the null hypothesis that mu1 is equal to mu2. Well, math, where you just slide that over, becomes negative, or subtract the mu2 from both sides. If those were equal to each other, when I subtract them, I get 0. That's what I'm going to plug in for my mu sub 0. So I'm saying 0 because I'm assuming there's no difference in the two populations. It says list 1, wait, my stuff's in list 3, so let's go second list 3. And then I come down. I had a less than, remember, as our alternative hypothesis, so make sure to choose that. And I'll go down and calculate. Again, you'll probably need both of these numbers. I'll jot them both down like I typically do. So the calculator's probably, not the calculator, the online homework's probably going to ask you for the t-value and the p-value. So the t-value, if we go to 2 decimal places, that 69, I go to the next numbers, the 6, I have to round up the 9. So the 69 turns into a 70. So negative 11.70. The p-value, notice it's 4.8, but you can't have a probability that's 4 point anything. A probability always has to be below 1 or below anyway. But at the end it says e to the negative 7. That means I have to move the decimal 7 places. Let me show you with that p-value what that means. So this negative 7, here, let's erase what I have on there so far. This negative 7 need to take the decimal and move it 1, 2, 3, 4, 5, 6, 7 places. That's the new place the decimal is going to go. So I'm going to have 6 zeros here. And so if I round that to my typical 4 decimal places, the next digit doesn't even round that up. My p-value in this case is be 0.0 with 0.000 to 4 decimal places, just 0. So there's my p-value. So when I flip over, let's go ahead and clear this. Now I've got all the information I need, all my statistics. So now let's flip back over and write this down. Stop share. That is not what I wanted. Share screen. Let's go back to the screen. Okay. Let's pull up our working papers, which is that. Is that going to pull it up for you? There's a little lag here, I see. There we go. Okay. So we found out, let's go ahead and write this down. I said the t-value was negative 11.7. Think about what that's telling us. It says the t is the same as the z value. It's just calculated a little bit differently, but it stands for the number of standard deviations from the mean. So we're saying under the assumption that the population means are equal, we would have gotten this, we're 11.7 standard deviations to the left of the mean. Well, remember, if this is normally distributed, which has to be the case for us to do any kind of a t-test, 99.7% of the data is within 3 standard deviations. We're almost 12 standard deviations away, which is why our p-value is essentially 0. So our p-value, we got that 0.0000, and we see if that's less than or equal to, well, we go back to what alpha was 1%, 0.01, and clearly it is less than that. So I was going to say I'm only going to reject the null hypothesis if the difference between these two groups, the cold water and the ice slurry, if that value, under the assumption that the means are equal, would happen less than 1% of the time. Up to 4 decimal, it happened 0% of the time. So we say, wow, that is really rare. So I'm going to reject the null hypothesis. Again, remember, this value right here, essentially we can think about that as the probability that the null hypothesis is true. So there's almost 0 chance the null hypothesis is true. That is why we reject the null hypothesis. So we say, I don't think that they're equal. So I have to go with the alternative. And then I answer the question. I say, oh, yes. It appears that, let's move that, minutes to fatigue with ice slurry is less than, minutes, is less than with, ooh, I said the wrong thing right there. Dang it. Let me erase that. Let's get our sentence correct. let's see, I need to erase this because population 1 wasn't ice slurry, population 1 was cold water. So it appears that minutes to fatigue with cold water is less than with the ice slurry. Ta-da! We are done. Now, I'm not asking you in this section to do any confidence intervals with these. The only problems from this section will just be hypothesis testing. And in fact, the last problem on the homework in this chapter was a confidence interval. I did not like the wording, the conclusion of the confidence interval, so I threw that problem away. Okay, so there's one of our problems. We'll do another one to get a little more experience with this, but that's the idea. All right, so let's go on to the next problem. We'll click over here so that we can pull up another problem. I'm pulling up problem 10-157, if I can. 10-157. Let's see. We'll just copy it. And then we'll go back over, paste it in. Okay, so there's our problem. So let's take a look at this one. It says anorexia treatment. Anorexia nervosa is a serious eating disorder, particularly among young women. The following data provide the weights in pounds of 7 anorexic young women before and after receiving a family therapy treatment for anorexia nervosa. Okay, so they give us the data and then it says, does family therapy appear to be effective in helping anorexic young women gain weight? Perform the appropriate hypothesis test at the 5% significance level. So we know 5%, so we know alpha is 0.05, so we've got that going for us. Now, again, these are related to each other because these are the same, it's the same person before as it was after. Now, that's why these are related. So same person, so it's not independent. And since it's not independent, use paired t-test. Not two sample t-test, just a regular paired t-test. I don't know why I can't spell paired, but just a regular paired t-test. So in the calculation, okay. But now here's what we're going to do. We're going to subtract again to get the differences, but I'm going to change this a little bit. I'll show you why. If I do before minus after, notice if I just look at that first one, and then I'll erase this in just a second, but if I 83.3 minus 94.3, so if I do it in the order we did last time, I'm going to get a value of negative 11.0 if you want to keep that going. But to me, if we're talking about somebody's weight and I get a negative, in my mind, I'm thinking they just lost 11 pounds. Where really gained 11 pounds. So this number seems to me not to be an accurate way of looking at it. So when we have a before and after situation, I'm always going to switch it around and I'm going to do after minus before. So after minus before. Because now if I get, in this case, I'll get a positive number, it'll mean that that particular person gained weight. So you don't have to do it that way, but you have to be very careful with your alternative hypothesis if you don't. And I'll tell you why, because here's what it says. Does family therapy appear to be effective in helping anorexic young women gain weight? So if we're saying gain weight, a lot of people are going to look at this gain weight and think positive. But if I do before minus after, I'm looking for a negative number that I have to do a less than. I think, again, when we see gain weight, we think, oh, the null hypothesis is going to be that mu1 is equal to mu2. But the alternative hypothesis is that mu1 is greater than mu2. That's not what we're showing. They're gaining weight. It's actually the other way around. So we're actually doing a mu1 is less than mu2. All right. So that's what we're doing. If they've gained weight, they weighed less before. Okay. So now if I do the after minus before, I'm looking for negative numbers. So to me, it makes more sense. So let's look at this and check to see what's happening. Okay. So I'm going to enter, and there's a lot of numbers here and there's a lot of decimals. Obviously, you can't do this, but I'm only going to use the first two columns of numbers just to understand how the problem's done. I don't think me putting in all the numbers is going to help you understand the problem any better. But realize by doing this, I'm not actually getting the answer to this particular problem because I'm not using 17 anorexic young women. I'm only going to use the first 6. So hopefully you will forgive me for that. But that's what I'll do so you don't have to be bored watching me put so much stuff in there. Okay, so let's do this. I'm going to do a new share. And the share is going to be calculator. So hopefully that came up for us. There it is. All right. So let's go in. I'm just going to put those first two columns of numbers in. So the before number, so let's go stat edit. I'll clear each of these. Clear that. And I don't have 10 values, so I'd have to delete the numbers below that. I don't want to have to do that. So 83.3, 86.0, we'll just put in 86, 82.5, 86.7, 79.6, 87.3. Okay, that's all I'm putting in for my data for the first, well, for the first weighing, the before. And then I'll go up here. We'll clear that list out. I'll put the after weights of these same 6 women. 94.3, 91.5, 91.9, 100.3, 76.7, and 98.0. We'll just put in 98. Okay, so there's our data. Again, I'll go over to list 3, this time doing after minus before. Again, the reason is if I did before minus after, when it said that they gained weight, I would have to make that a greater than. So you can do it that way, just make sure your inequality is facing the right way. So I go back to list 3. I have to re-put it up there because it just put in the numbers. So I have to go in and actually put L2 minus L1. Notice it's not doing a calculation. So I go second L2 minus second L1, and then I get a new column of numbers. Okay, so look, notice the positive numbers. Most of the young ladies gained weight. One of them actually lost 2.9 pounds. And we can see that because her after weight was less than her before weight. Okay. This is not working out well for me. Here's what I'm going to have to do. Since these are positive numbers, remember I talked about, we're going to have to scratch everything I just said. I apologize, but it won't be a hard deal. Let's do this. If we were looking at the differences in the numbers and actually calculating the difference and saying is the difference positive or negative, then we would need to do this. But in this case, actually, all we need to do, we're still just going to do L1 minus L2. Oh, that's not what I wanted. Quit, second quit. Am I back? I need to go back. Okay. Stat. Okay, go back to L3. Second, let's do L1 minus L2. And I'll tell you why we're doing that, and I apologize. So what we're doing here, since we did change that inequality to a less than, we are looking to see if the numbers were less than afterwards. So if they're less, we're going to get negative numbers. So this will tie into the way we set up our problem. And since I already set that up as a less than, that's why we'll do L1 minus L2. So we'll keep that consistent. Okay, so now I'm going to do the test again on L3. It'll be nice because we're already have that written down. Again, remember we're doing a t-test because their samples are related to each other. We come down and we had a less than again. Notice L3. Notice that we're assuming the differences are 0. Again, we had a less than. We'll go down, we'll calculate. We'll get both our p-value and our t-value. This time the t was negative 3.27 and the p was 0.011. All right, so let's go back. Let's stop that share. Well, that's not the screen I wanted. So share screen. Oh, we just need to select that. So there's my sheet. So now we can write things down. So we got a t-value of negative 3.27, but our p-value, which is what we really care about, is 0.011. We compare that over here to my alpha, see if that's less than or equal to 0.05, which was my alpha. And again, it is. Let me erase that mark. So it is less, so we say reject the null hypothesis. So if the weights were the same before and after, we would have gotten this much difference between the two that we got only 1.1% of the time. Again, if it helps you change these two percentages, 1% and 5%, that's easy to see that, oh yeah, 1% is definitely less than 5%. So we reject the null hypothesis, so we don't think the means are equal. We don't think the young ladies weighed the same before and after. So we answer the question. It says, does family therapy appear to be effective? Yes. Family therapy does appear to be effective. In helping young, anorexic young women gain weight. Oh, wait. Okay. So let me restate this because I was a little confusing with the L1 minus L2 or L2 minus L1. What we can do, since we're writing our hypotheses the way we did up here, with saying, oh, population 1 mean was less than population 2 mean, we can always just do L1 minus L2. So we don't need to worry about switching that. So always just do L1 minus L2. You should be fine with the way we're stating our hypotheses. there's another way of stating hypotheses where we just list the difference instead of the two populations, but our author doesn't do it that way. So we, with this author in this book, can always just do L1 minus L2, and we'll be in good shape. Okay, so that is that. We're finished. I gave you a couple examples, and truthfully, after one example, we probably would have been fine because they work the same way each time, and just work on these. I think you'll get them pretty quickly. There's about 4 problems in the online homework from this section, but I don't think that's overwhelming because I think you'll click through them pretty quickly. All right, well, that's it. Hopefully it made sense to you and I didn't confuse you too much. And with that, we're going to stop here, and I will see you virtually on Tuesday.